Welcome. So, till now what we have done? We have done Fourier analysis for 2 pi periodic function and then the Fourier analysis for the group Zn. Now, if we want to generalize this concept to other setting, then let us see that what are the building blocks we have used and what are the commonalities between these two settings what we had developed. So, like for example, I mean in the Fourier 2 pi periodic function, if I am taking identifying with the 0 1 this as a group, it is a sum modulo 1 with. So, now I can identify that with this. So, that means if we look at the map e to the power 2 pi I x, then this is going to this we are identifying one periodic function, there it will be going to be one periodic, or if I want to get 2 pi periodic, then as we have discussed earlier, then this is e to the power I x, then I can identify with this open in the unit circle with 2 pi periodicity. Okay, so, for the time being we are identifying this. So, now this is the unit circle, let me call this T, that can be identified with S1 mod Z is equal to 1. And now, this is a group, because all the elements is going to look like e to the power 2 I theta and then e to the power 2 pi I psi, this is equal to e to the power 2 pi I theta plus psi, and as you can see that theta plus psi is the sum modulo 1. So, we did the Fourier series with this. In this setting. Now, next what we did, we take the unit circle, then we take the nth roots of unity. So, here this we have seen that we have identified with Zn, these are all the nth root. So, we did, and this also we have seen that this is a group under sum modulo n. So, this is a finite group, this is an infinite group, and both of them are abelian group. So, now if we are interested to generalize, then one would like to say that okay, if I have an abelian group, then can I do Fourier analysis there. Now, what is the building block to do Fourier analysis? Here what we have seen in the Fourier series case, let us say call it for circle, the main important thing is that e to the power n theta, this is e to the power n, theta, I am taking e to the power 2 pi I n theta. Now, in Zn, our building blocks what we have seen, let us say e to the power n of k, this is equal to e to the power 2 pi I k n by n. And these two functions with in this setting with this and this, we are able to derive satisfactory Fourier analysis result what we got it for the Fourier series and this. So, it is natural to us to search for such kind of function which is needed for our setting for G is an abelian group. Now, for the time being, let us concentrate if G is a finite abelian group. Let G be a finite abelian group. Now, what is the feature of this? Now, the feature of this is that all these maps, they satisfy if I am using a universal symbol for both the maps E n, then phi acting on the group element x plus y, this is going to give me phi x into phi y, and this phi is a map from, let us say, this either t or z phi of x mod is 1. So, now in other words, this is preserving the group property, because we are considering circle as a group. So, now this is from circle to circle, which is preserving the structure of the homomorphism, because in the circle if you take e to the power I t e to the power into e to the power I s, then this would be e to the power I t plus s. So, that is where this symbol is coming from. And now, so what kind of map this is going to be? Let us first see lemma. Let G be a finite abelian group, and gamma from G to some complex number G to C a function such that gamma of x plus y, this is the plus is the operation of the group G, I am denoting it as plus, which is equal to gamma x into gamma y, these two are the complex number, and gamma of E, E is the identity, E is the identity of G. Then mod of gamma of x, this is automatically goes to the unit circle for all x belongs to G. The proof is simple for finite groups, because if let the cardinality of G is n, then by the Lagrange theorem x to the power n is equal to identity for all x belongs to G. Now, I apply gamma of x to the power n, which is equal to gamma of x to the power n, because gamma x to the power n is gamma of x plus x n times. So, which is because of this property what we had been given, this will be gamma x into gamma x into gamma x n times. Therefore, this identity holds. Now, this is equal to gamma of E, and given that this is 1. Now, for you take any x, then gamma x to the power n is nothing but 1. So, gamma x is an nth root of unity. Hence, mod of gamma x, this will imply mod of gamma x, this is equal to 1 for every x belongs to G. Okay. So, now one of the observation what one can get observation, let phi is a map from finite abelian group to some C minus of 0 such that phi of x plus y, this is equal to phi x into phi y. So, if I am assuming that it is going to the punctured complex plane, then phi of x, this is automatically 1 for all x belongs to G. Why is so? Now, let E be the identity. Then phi of E, this is equal to phi of E plus E, because E is the identity with the group operation, this is same. So, which is equal to phi E into phi E, which is equal to phi E square, and phi E is a complex number. So, phi, if once phi E is a complex number, therefore, phi E is equal to 0 or 1, because z square is equal to z can only happen z equal to 0 or z equal to 1. Now, since phi is a map whose range does not take the value 0, this will imply phi of E is equal to 1. Hence, by the lemma we will get that mod of phi of x is equal to 1. Hence, by lemma so, essentially if we get this as we know, this is C minus 0 is a group under multiplication. So, now if I have a homomorphism from the finite group G to C minus 0, then this is automatically is going to give me that mod of phi x is equal to 1 if I have G is a finite abelian group in this for our setting. Okay. So, now let us collect all those. Let me denote for a given G a finite abelian group. G had the set of all gamma G to C such that gamma, or rather I can take it now all gamma G to T, that means mod of gamma x is equal to 1 x plus y, this is equal to gamma x into gamma y. Obviously, this is a non-empty set because there is a trivial map. If all these elements are mapped to 1, then that is going to be true. Okay. So, before making more progress into this, so let us try to look at some concrete example of finite abelian group. So, which would be useful, let us say example. What we always have is of course Zn, that we have dealt with. Now, what are the other one? So, it is related to that. So, now if I take Q belongs to Zn, or rather I take just Q is in N, and then if M1 and M2 belongs to ZQ, then I can define M1 into M2, and this is going to belong to again ZQ. Why is that? I mean, it is very simple. Then M1 is equal to some K1 times Q plus L1, where L1 lies between 0 to Q minus 1, and M2 is equal to K2 Q some into L2. L2 is lying between 0 to Q minus of 1, and K2, K1 are integers. Now, if you do the multiple M1 and M2, then what you are going to get is K1 K2 Q plus L1 K2 plus L2 K1, this Q plus L1 into L2. Now, L1 and L2 are the positive non-negative integers. So, now this I can write it L1 and L2 sum n q plus r, where r is going to vary from 0 to q minus of 1. So, therefore, this is in this form. So, that is pretty easy. So, we have this is. Nevertheless, now if I want to make it a group, then what I need is an identity element and inverse of everything in the multiplication. So, like what we have seen in R may not be a group, although the multiplication is defined, but if I take out the 0, then that is going to give me. So, now towards this end, let me define so definition, we say an integer m belongs to ZQ is an unit if there exists a n belongs to ZQ such that m n is congruent to 1 mod q. That means m n minus 1 is divisible by q. So, now I denote z star of q, this is equal to set of all m belongs to z q such that m is a unit. Now, let us look in particular case z star 4. Now, you see z 4 is equal to 0, 1, 2, 3. Certainly, 0 is not going to be a part of z star 4. So, and 1 into 1 is 1, 1 minus 1 is 0 divisible by q. So, this is 1. And now, 2 is obviously whatever you multiply, this is an even number. So, you subtract 1, it is an odd number, can never be divisible by 4. So, now this, if I take 3, 3 into 3 is 9. So, 9 minus 1, 8, this is going. Now, if you look at z star of 5, this is equal to 1 would be 1 definitely. And now, if I take 2, then 2 into 3 is 6, 6 minus of 1 is 5, which is divisible by 5. So, therefore, 2 and 3 would be there. So, now z 5 is equal to 0, 1, 2, 3, 4. Now, what about 4? 4 into 4 is 16. So, minus 1 is 15. So, that is also an unit. So, z star 5 is now 1, 2, 3, 4 except the 0. So, essentially you can see that z star of 5 and z 4, the 0 is going to 1, 1 is going to 2, 2 is going to 3 and 3 is going to 4, then that is giving you an identification of this. So, similarly, if you look at z star of 10, so this is equal to, of course, 1 would be there and then 3 into 7. So, 2 will not be there because of whatever you do, you are going to get even number, and 3 and 7 this will come. So, and then 4, 5 will not come, 6 will not come, 7 is there, 8 will not come, and then 9, 9, 81. So, this is what we are going to get this. So, now we will have some other example other than the Zn as a finite abelian group to do some Fourier analysis, and there will be lot more. Now, recall that what we have defined the g hat for a finite abelian all such gamma from g to t such that gamma of x plus y, this is equal to gamma x gamma y. Now, if G is a finite abelian group, then what we can observe that that G hat is a finite abelian group. Okay. Under operation I need to give under pointwise multiplication, that is, if gamma 1 and gamma 2 belongs to G hat, then we define gamma 1 gamma 2 this as acting on acting on G, this is by definition is gamma 1 of x, gamma 2 of x. Then certainly if gamma 1 and gamma 2 are belong to G hat, then gamma 1 gamma 2 this is a map from G to C. So, now what we need to check is that this satisfies all of this satisfies this property and mod of this is 1. Now, in order to be a group, first we must say that this gamma 1 gamma 2 that belongs to G hat. So, now in order to do that gamma 1 gamma 2 of x plus y by definition is gamma 1 x plus y, gamma 2 of x plus y, which is equal to gamma 1 x, gamma 1 y, gamma 2 x, gamma 2 y, and all the complex number multiplication I can change the order of the multiplication. So, this is going to be gamma 1 gamma 2 of x by considering these two and gamma 1 gamma 2 of y. Therefore, this satisfies this property and modulus of gamma 1 gamma 2 of x, this is equal to mod of gamma 1 of x, gamma 2 of x, and both of them are mod 1. So, this is going to be mod 1. So, now the closure is satisfied. Similarly, very easy to check that if gamma 1 gamma 2 gamma 3 should be equal to gamma 1 gamma 2 gamma 3. So, because of the complex multiplication complex number you can do that. So, the closure and associative is there. So, now one need to check the identity. Let gamma 0 of x is equal to 1 for all x belongs to G. Clearly, gamma 0 belongs to G hat. Now, if you take gamma gamma 0 of x, then this is equal to gamma x gamma 0 of x by definition, which is equal to gamma x. So, now you multiply gamma 0 on any member of G hat, then what it is going to give you is returning you back the gamma x. So, hence that is the identity. Now, existence of inverse, that is what one need to check. So, existence of inverse is going to be, so now define gamma star of x, which is equal to gamma of x bar. Now, clearly gamma star of x plus y, which is equal to gamma x gamma y bar, which is equal to gamma x bar gamma y bar, which is equal to gamma star of x gamma star of y, and now mod is 1 of course. So, now if I take gamma gamma star of x, this is going to be equal to gamma of x into gamma star of x by definition. Now, this is going to be equal to gamma of x bar Now, this is going to be mod of gamma x square, which is equal to 1, which is equal to gamma 0 of x, the identity. So, therefore, for every gamma in G, there exists an inverse, and we can write the inverse gamma star as gamma bar if there is no confusion arise. Okay. So, now what are the, so now we have the building blocks. Now, what do we want to check, that whether they are the correct ones or not. Now, one of the most fundamental properties what we have used in the Fourier series as well as in Zn, that there is some orthogonality relationship between all these fundamental blocks. So, they are pairwise orthogonal, and in fact, they were orthonormal. Now, in order to talk about the orthonormality and all, like in the Zn case, so we will define a vector space and an inner product, and with that appropriate inner product we will show that all these they are orthonormal. Now, all this gamma belongs to G hat, we will call gamma is a character of a finite abelian group G. For each G, now we have the set of all characters, that is a homomorphism from G to the circle group. So, important question is that one would like to ask that if G is a finite abelian group, what we have proved that G hat is also an abelian group. Now, is it going to be a finite abelian group or not? And so, that's, and then whether all these characters they satisfies orthonormal relationship with an appropriate vector space. The vector space is natural, that we would like to consider the set of all functions from G to C, and in that natural to define the inner product, and we will check that with that inner product whether these gammas they are satisfying orthogonal relationship or not. Thank you.